Good afternoon, Caleb. How are you doing this afternoon? Caleb, can you try to use your mic and see if I can hear you? If not, I'm going to jump out.
Hey, how's it going? Can you hear me?
All right, I do not hear you. All right, I'm going to jump out and jump right back in. 1 second. All right, Caleb, let's try this one more time. See if I can hear you.
All right, can you hear me?
I can hear you now. Awesome. Hopefully you had a great weekend. Oh my goodness, the weather this weekend was just amazing.
It was wonderful, yeah.
Were you able to get out and do some stuff?
Yes. Spent some time practicing unicycling outside, went for a couple walks.
Awesome. Yeah, it's kind of raining today, but it's a school day, so no biggie. All right. It's 4 o'clock. Let's see if Henry will join us. I'm sure he will in just a bit. Let's start anyways, because there's a lot of stuff to get through today. Last week we were talking about what were we talking about? Vectors, or I think we were talking about vectors last week.
Yep.
It seems like every week just molds into one. All right. Here's a review problem. It says an object in motion in the plane has acceleration vector of sine of t e negative t, e raised to negative t for time 0 to 5. It is at rest when t is equal to 0. What is the maximum speed it attains? All right. So the first thing I would do on a problem like this is I'd try to find the velocity vector. Since this is an acceleration vector, my velocity vector, oops, I better turn on my marker here. My velocity vector is going to be, what is it, cosine of t, comma, e to the negative t, or should it be -1 in there? I think it should be negative 1 e to t. Something like that. And then if I want to find the, what was it, the speed of that it attains, that is the absolute value. So I'm just going to end up with the square root of cosine of t plus 1 squared plus, now where did I get the plus 1? I forgot. We should have did this one, so we end up with cosine of t plus c, but then we have to, it's at rest at 0, so I should have solved for my c value, which is 1 in both of them. So that should be plus 1 in here when you think about it. And then I would end up with e to negative t plus 1 squared. And I believe if you work this out, I think the answer should be, if my notes are correct, I think I worked this out, I think it's 2.27. Maybe it was 2.17. Can't read my writing. It looks like a decimal point in there. So letter C should be it. And there is the answer. I guess it was 2.17. All right. Now this one's a little bit tougher, but it's not too bad. It says the figure above shows the path traveled by a roller coaster car over the time interval between 0 and 18 seconds. And then it says the position of the car at time t seconds can be modeled by parametrically by the equation. And this is where it gets really crazy. x of t is 10t plus 4 sine of t, and y sub t is 20 minus t times 1 minus cosine of t, where x and y are measured in meters. The derivatives of these functions are given. Okay, so they give us the derivatives. X prime of t is 10 plus 4 cosine of t, and y sub t is 20 minus t times sine of t plus cosine of t minus 1. Part A, it says find the slope of the path at time t is equal to 2. Show the computations that lead to your answer. Okay, so find the slope of the path at time t is equal to 2. So what I did is I just did y prime of 2 over x prime of 2, which you can plug all those values in, but I believe it comes out to be like 1.794. So finding the slope, parametric equation, just y prime over x prime, and we're trying to find it at 2, so we just plug in 2. Part B, it says find the acceleration vector of the car at the time when the car's horizontal position is x equals 140. Okay, so in this problem, it's like, okay, so I'm finding the acceleration vector of the car at the time when the car's horizontal position. So horizontal position is going to deal with the x value. It's not going to deal with the y value. So all I did is I just said x of t is equal to, and they gave me the 10t plus 4 sine of t, and I set that equal to 140, and then I just solved that. Now, obviously, this is a calculator type problem. Probably would not be able to solve this without a calculator. Let's see, nah, I'm looking at it. There's no way I'd be able to solve that without a calculator. So I would just plug this into my calculator, and I believe you get t is equal to like 13.64 or something like that. And then the last problem, it says find the time t at which the car is at its maximum height and find the speed. Okay, so we want to find the maximum height there. So this time I'm dealing with, I'm just dealing with y prime of t, and when it's at its maximum height, shouldn't y prime of t equal 0? So then I just set y prime of t is equal to 0, and I solved, and that is it. I mean, the only problem, the only reason I went through a problem like this is because obviously there's parametric equations on the AP test. And the more you see them, the better off you're going to be. Any questions on that, Caleb?
No, that makes sense.
All right. So here's all the work, all the point values for them. Oh, I forgot to do the speed, the average speed. All right. Today, we are going to be dealing with polar functions. I'm going to spend probably 10-15 minutes just on what are polar functions, how to come up with the values of a polar function, and then I'll talk about the calculus with polar functions, okay? Just like we've done for the last 3 weeks. We kind of first talked about vectors and parametric equations, and then we talked about the calculus that goes into them. The calculus with polar functions is a little bit more extensive because we're going to be finding the derivatives of polar functions. We're going to be finding the area between curves, and we're going to be finding the length of a curve. Okay, so there's a couple things that will be calculus based when we do this. All right, so that's what we're going to be doing. So polar coordinates. If you graph the two functions y is equal to sine of 3x and y is equal to cosine of 5x on the same pair of axes, you will get two sinusoids. But if you graph the curve defined parametrically, and that's where it gets a little bit interesting, we graph parametrically, we would get a graph that looks something like this. Another way to enter that world is to use different coordinate system. And that's what we're going to be talking about today. It is called the polar coordinates. Have you ever seen the graph that looks like this? It has circles instead of... If you ever seen a piece of graph paper that has circles on it, you're talking about polar graphing then, okay? And we're going to be trying to figure out how to graph polar coordinates tonight or today. So a rectangular coordinate, it's just an x and y value. Okay, you're given, so you go over 2, you go up 2. That is a rectangular coordinate. Now, if I wanted to get to the same spot in a polar coordinate, well, that is r and theta. What is r? R is the distance, the hypotenuse, basically, when you think about it. So if I had the same, because I'm really graphing the same point, it's just I'm getting there in a little different way. So if I graph this, if this was 2, a squared plus b squared equals c squared, this hypotenuse would be 2 square root of 2. So that is your r value, and your theta is going to, or your y value is the angle that you would take. So this is the distance, this is the angle. So pi over 4 is 45 degrees. That kind of makes sense, right? So if I wanted to graph that little point right there in a polar coordinate, that point would be 2 square root of 2 pi over 4, or 45 degrees. And it would give you the same point as on a rectangular coordinate. So that is a polar coordinate. Now, these are really, really important. The x value, okay, the x value of a polar, this is called a polar rectangular conversion formulas. These are pretty important. And if we go back to our same graph of before, this was 2, 2. And in polar coordinates, it was 2 square root of 2, 45 degrees, right? Okay. Well, if you think about it, if you wanted to get the x value, all you do is you multiply 2 square root of 2 times cosine of theta. So what is, if you did cosine of 45 degrees, what is cosine of 45 degrees? If you remember your special triangles, okay, cosine of 45 degrees is 2, cosine of 45 degrees is 2 over 2 to the square root of 2, right? So if you took r, which is, what did we say r was in this problem? 2 square root of 2, times the cosine of theta, which was 2 square root of 2. Guess what? We came up with our x value, which would be 2. So if I wanted to convert a radian measure to a rectangular measure, I use this formula. And I could also go backwards if I wanted to find my polar coordinate and they gave me an x value, I can still find the polar coordinate. So these are really, really important. So are these. But this one is pretty straightforward. R squared is equal to x squared plus y squared. That's Pythagorean theorem. Finds the r value. And then tangent of theta, the angle, is just y over x. When you think about it, we had that point here, and this was 2 and 2. Tangent of theta is equal to 2 over 2, so tangent of theta is equal to 1. If you take the inverse tangent, you get 45 degrees. So these are ways that we can convert rectangular coordinates into polar coordinates. Okay? Really, really important to know those, because when we start doing some problems, you're going to have to start converting. All right. Find two different sets of polar coordinates for the point with the rectangular coordinate negative 3, 3. Okay, so rectangular coordinate, so negative 3, 3. If I put that point there, negative 3, 3, I could come up with thousands and thousands of polar coordinates that would end up right there, right? Because you could just keep going around and around the circle. It doesn't make any difference. But if I was going to do negative 3, 3 and I wanted to find the polar coordinate for it, well, the first thing I want to do is I want to find my r value. So r squared is equal to x squared, so that's going to be 9 plus 9, take the square root, so r is equal to the square root of 18. And what is the angle measure? Well, when you think about the angle measure, now we could take 135, 135 degrees. That would get us to this point. I could go all the way around the circle again. I could go backwards. What would that be? 180 plus, so that would be a negative 225. That would also give us, it would stop in the same spot. Okay, so anytime you take that angle there, you should be able to find the value of that.
Mr. Shanklin?
Yep.
Can you have a negative radius? Like, could this be said to be negative 45 degrees and the radius be negative square root of 18?
No, the radius has to be positive because distances always are positive. Now, in most of the times, we don't even use negative angle measures. I was just saying, in this problem, it says you can go around the circle. They wanted you to find more than one point that would end up in the same spot. Well, so I could go negative, I go positive. Usually, we do not do negative angles, and never is the R value going to be negative because that is always going to be a distance. Okay, but in order to get to this point here, I could have. This is just, as I said, we're just kind of trying to explain what polar coordinates are right now. So if I gave you this problem here, okay, find the rectangular coordinates for this. Okay, so I'm going to let you do this one. This one's a pretty easy one to find the rectangular coordinates if you understand what we're doing. So what would the rectangular coordinates of this problem be?
X would be 0 and Y would be 4.
Yes, exactly right. It would, because if you graph this thing out in polar coordinates, 4 pi over 2 is going to be this way, and then 4 up is going to be right here. So this value here is 0, 4. Yeah, so changing from a polar coordinate to a rectangular coordinate, yeah, it's not that bad. I mean, especially if you can visualize where it's ending up. I mean, it's not bad at all. Okay. Now, it gets a little bit more complicated when we start graphing all the points in the plane that satisfy the given coordinate. Now this is like, all right, so if I wanted to graph all of the points that r is equal to 2 in a polar coordinate, what do you think the graph would look like?
It's a circle with the radius as 2.
That's exactly right. Circle with the radius of 2. If I had negative 2 as r, same thing. It doesn't make any difference. It's still going to be a circle with negative 2. I'm sorry, with 2, not negative 2, because the distance is always going to be the same. How about what is the polar graph going to look like if theta is pi over 6?
Just a straight ray?
That is exactly right. It would look like this. 30 degrees. Boom. That is it. Very nice. Okay, and here's basically what they would look like. All right. Now, this one gets a little bit more difficult. It says, find an appropriate graphing window and produce a graph of the polar curve. Okay, so you have a graphing calculator, correct?
Yes.
All right. So we're going to go into mode right away, and we're going to put it into polar coordinates. Okay, so you should have something on your calculator that says POL or something like that. That means it's going to be polar coordinates. So what we're going to do is we're going to graph this function, okay, sine of 6 theta. Okay, so I'm just going to type in sine of 6 theta into my calculator. And the graph that I get, uh-oh, no, not. My calculator is a little slow and old. I'm going to put it in Radian modes, though. It might help. All right. Radian mode did help. However, hang on. Better change my max min. I'm not sure. Let's see here. All right. So what did you get for a graph?
A rather sporadic flower-esque looking
Something
thing.
like this?
Yes. The
Okay.
one on the left.
Yes, that is the correct graph. Mine, it was so I don't think I should have zoomed in because mine was a little bit really dark. I mean, it looked like it went, but there's a lot of leaves off of that thing. So that definitely is the reason why it looks so weird on mine. So if you put in the next graph, 1 minus, I'm going to put this one in because that one's a little bit that one should be a little bit easier to see. 1 minus 2 cosine of theta, 2 cosine of theta. Just want to make sure my calculator is graphing it correctly. Yes, woohoo! I got that one. Okay, so you can definitely graph these things using your calculator. Okay, and it should look something like this. And the last one, I don't remember what the equation was for the last one. 4 sine of theta should look something like this. So you should be able to graph functions in with polar coordinates. Okay, and that is how you do it on your calculator. Just change it to polar coordinates, and you should be able to get the graphs. All right, now let's talk about the calculus with polar functions. Okay, so since polar curves are drawn in the xy plane and the slope of a polar curve is still the slope of the tangent line, which is dy dx, the polar rectangular conversion formulas enable us to write x and y as functions of theta, so we can find dy dx as we did with parametric defined functions. Okay, so dy d theta over dx d theta is going to be how we find a derivative of a polar function. But sometimes it gets a little complicated because you're going to have to change your functions. So let's take an example. It says find the slope of this polar curve. So it says find the slope of the rose curve. Okay, so this is the rose curve. It's a very this one is used a lot. Okay, r is equal to 2 sine of theta, 3 theta, at the point where theta is equal to pi over 6, and use it to find an equation of the tangent line. Okay, so what do we need to know here? We need to know, we have to find out x and y. Okay, but remember, we said that x is equal to r cosine of theta, and we said that y is equal to r sine of theta. Okay, well, they told us what r is, so my x value is going to be, what is that, 2 sine of 3 theta cosine of theta? Is that right? So 2 sine of
Yep.
3 theta cosine of theta. And my y value is going to, and I should have put the y on top because it's y prime over x prime, but that doesn't make any difference. And then my other one is going to be, what do we have here? R, so that's going to be sine of theta, sine of theta. I believe. Oh no, that is not. R is, I don't know what I was looking at. I was looking at the same thing. Sorry about that. It's going to be 2 sine of 3 theta sine of theta. Sorry about that. All right, so here's my x value, here's my y value. So in order to find the slope, I need to go y prime over x prime. Am I going to be able to do this without a calculator? I'm not even sure we could, because even if we knew how to take a derivative or an integral, no, a derivative, sine of 3 theta cosine, yeah, I guess we could, because we would just use the chain rule. Yeah, not the power rule. We'd have to use the chain rule, won't we? Because you've got two. Yeah, the product rule, because you would go u is equal to sine of 3 theta, u prime. I could have put the 2 in. I could have put the 2 in there too. U prime would have been 2 cosine 3 theta sine. So we could do it, but these are, I would say, 99.9% of the time, these are calculator-based problems. So I would not, I would not spend the time trying to work this out, because then you're going to have to plug in pi over 6, and it does work. I mean, it does work. You can do it. I guess I did do it by hand. It wasn't. I suppose it wasn't that bad, because when you plug it back in, so when you plug pi over, well, I guess we do have to plug it back in to get our point, right? Because we do need a point and the slope. So if I wanted to find my point, I'm going to have to plug in pi over 6 here, right? Well, what is pi over 6? Well, it doesn't really matter, because this is going to be 2 sine of 3 pi over 6. Well, that's going to cross off. That's going to be pi over 2. So really, I have sine of pi over 2. Well, a quick graph of that. Sine of pi over 2 is 1. So 2 times 1. So this is going to be 2. And then cosine of 30 degrees. This pi over 6 is 30 degrees, isn't it? So that would be, let's see here, 2 square root of 3. So is that 1/2? Sine of 30 degrees, or cosine of, cosine is square root of 3 over 2. So this would be 1 and then square root of 3 over 2. So coming up with your point, and you can do it without a calculator, it's going to work, but I would definitely use a calculator instead, because it's going to help out immensely in there. All right, so I think the next slide has the work for it. So here's the work, the derivative, 2 sine 3 theta sine 3 theta, blah, blah, blah. So they ended up with negative 1.73205. Okay. Any questions on finding a derivative of a polar coordinate?
No, it seems to go along pretty well with what we've done so far.
Yep, exactly. It's just the only hard thing, I think, is that you have to know the x, how to come up with an x and y value. Okay, so that's why I said those two were pretty important. You need to know x is equal to r cosine of theta, and y is equal to r sine of theta. Okay, so those two are really important. All right. So now we're going to talk about finding the area enclosed by polar curves. Okay, so we have two polar curves. We want to find the area between them. I guess this time it's just the area. So it doesn't change much from finding the area between two curves. For example, if I'm just dealing with the rectangular coordinate and I had a function like this and another function like this, we always did top function minus bottom function, right? To find the area between the two curves. Well, it's very similar, but instead of using rectangular objects, we're going to use what are a sector, and then we're going to add all those together. So the formula is fairly similar to what we did before. So what we're going to do is the area is going to be 1/2 times radius squared d theta. Okay, and again, this is going to be my r squared theta. So that is how we're going to find area. And if we want to find area between two curves, it's just going to be top minus bottom, or if it was something like this, it would be left minus right. So here is the formula to find the area between the curve, and it's just 1/2 times radius squared d theta. And this, I think this one makes it a little bit easier because you get the function in there instead of the r. All right, so let's take an example. So in this problem here, it says find the area of the region in the plane enclosed by the cardioid. R is equal to 2 times 1 plus cosine of theta. Okay. Now, when I set this problem up, first thing I'm going to do is I'm just looking at it, and it's like, okay, so you start here, you're going to go all the way around. So I'm going all the way around the circle. So I'm going to go, my integral is going to be from 0 to 2 pi. I'm just going to do 1/2 times 2, 1 plus cosine of theta, and that is going to be squared. Now, obviously, this is not something that I want to work out by hand. It would probably be pretty tough. So again, I'm just going to plug this into my calculator to come up with the answer. And I don't think I plugged this one into my calculator to come up with the answer. So if you want to find the answer there, just plug it in. I wonder if the next slide probably has the answer to it. Yeah. So here, now they worked it out a lot by hand, which I would not. I would have just plugged the whole thing in right away. Why do they have a 4 here and we had a 2? Well, remember ours had parentheses squared and the 2 out in front. They just squared that whole thing out, and then they took 1 plus cosine theta, squared it out. I wouldn't do it. I just would plug it into a calculator and come up with the answer. Okay, that would be a whole lot easier. And I would never ask you to do a problem like that without a calculator. All right. So the area between two curves is exactly like when we were finding area between two curves. It is top function minus bottom function. Okay, so top minus bottom, or if you're going from left to right, right minus left, right? Right minus left. And this is probably easier. It's big radius squared minus small radius squared, right? That's how we, or we can look at it that way. All right, so let's take an example here. Whew, look at this problem. So what they're looking for is they're looking for us to find this area right here. Okay, so let's find the area between two curves. All right, I am going to turn off my mic. I'm going to let you work a little bit and see if you get it correct. All right, so I'm just going to turn it off, let you work, see what you get for an answer. All right, because I've been doing a lot of talking today, so I'm going to let you do a little bit of work.
Sounds good.
Oh, I did not want to show you the answer. Sorry about that. All right, I'm going to turn off my mic.
I got an answer, but it's not right.
How do you know?
Because it's negative.
Yeah, you're definitely not going to get a negative answer when you're working on one of these types of problems. There's no question
Yeah.
about it. So let's take a
So
look.
I.
Oop.
Oh, never.
So how did you set it up?
Okay, so the one on the right was the one on the right was 1, and the one on the left was 1 minus cosine theta squared. So I did
Yep.
integral and then 1/2 of 1 squared, which is 1, minus 1 minus cosine theta squared. I put that into my calculator, put the upper bound as pi divided by 2 and the lower bound as negative pi divided by 2. You know what? I might have
Okay.
put those in the wrong spot.
Yes, because if you have to remember, the lower bound always has to be the smallest value. So the lower bound better be negative pi over 2. The upper bound better be pi over 2. That is the only way it's going to work here. I agree with what you said there, that the integral is going to what your integral was. I mean, there's no question, and let's take a look at the work that they had. I would say that you were right on. I don't know. Oops. Let's go back this way. So we're going to go the integral from negative pi over 2 to pi over 2, 1/2, and then 1 minus. Now they squared it out. I'm not sure why they do that. So it should have been, you should have had negative pi over 2 to pi over 2, and then 1/2, 1 minus, and then you're going to have parentheses here. And I forgot what the other equation was. 1 minus cosine of theta.
Wait, how did they get 0 as the lower bound?
I have no idea because they have the lower bound as negative pi over 2 here. Sometimes I don't understand what they do on some of their graphs. Because they brought the 1/2 out. It looks like they're just multiplying by 2 because the upper and the lower
Oh,
are the same. So they just
right.
put a 2 out here and then just said, oh, I'm just going to go from 0 to pi over 2.
This
I'm not
identity.
sure I would do that. I think I would just put it in this way. And then,
Yeah.
so what did you get for an answer? Let me just come. So the value that you should end up with, let's see. So this is pi divided by 4. So 1.21.
I'm trying to. Okay. Yeah, I got 1.57.
Did
Is
you
my
wait?
calculator on degrees? Oh my goodness. Let's see. No, it's on radians.
Okay. Let me put it into mine. I didn't put mine. I didn't put it in yet. So, do you still have your calculator in polar mode? I wonder if that makes a difference. So I'm gonna plug this in real quick. Okay, so I'm gonna go math. Mine is a little bit. Oh darn it! Sometimes I don't know how to use my own calculator. All right. So I'm going to put in the functions. So did you put the 1/2 in there when you put it in?
I put yes, 1/2 time the integral of 1/2 times 1 minus and then 1 minus cosine theta squared.
1 minus cosine. Yeah, there's a lot of
I
parentheses
have
in there.
exactly what you wrote up in the upper right hand corner.
Okay. Cosine. Then that's squared. And what did you get for an answer? Let's see here.
1.57.
All right. I think I have it correct so far. I'm just still typing in. I'm pretty slow at this. And then that was negative pi. You did negative pi over 2 to pi over 2, correct?
Yeah.
To pi over 2. Enter. Hate when I get errors. Oh, I think I forgot one. There's way too many parentheses sometimes. Like, no, let me
Mm-hmm.
insert a parenthesis here. Another one. That's a square here. All right, Mike is giving me an error every time I do it. I hate this TI-83. That thing is so bad. But if you plugged it in exactly like this, I know I'm not sure why you came up with 1.5. That doesn't make sense because it's exactly right. So you got the 1/2 times 1 minus cosine squared.
Mm-hmm.
That's correct. I mean, I don't know where, unless they made a mistake. I mean, it does happen. I mean, the book sometimes does make a mistake, but usually not. But that is exactly how you would do it. Not without seeing your calculator. I'm not exactly sure where the mistake is. So you got the 1 minus cosine. Yeah. So we set it up right. It's just who knows where the calculator is making a mistake. What type of calculator do you have?
I have a Casio.
Ooh. All right. Well, I won't even be able to answer any questions on the Casio.
Mm,
TI, yeah. Casio. I think we went through this last year. That
yeah.
Casio. You haven't got a new one yet? Come on. All right. So that's basically all you're doing with polar coordinates. All right. So the last thing, obviously, we're going to have to do the length of a curve also. So the length of a polar coordinate, okay, so, I mean, all of these formulas are super close to all of the other ones, right? Because you've got the length is going to be dx d theta squared plus dy d theta squared. Boom. Or you've got the, if you're going to use r squared plus dr d theta squared, that is the length of the equation. So if it's parametric, use this one. If it's polar coordinates, we're going to use this one. Okay, so let's take a look and see if I have an example. Oh, there's the formula, length of a polar curve. All right. Oh, no. No. It was supposed to be an example without the solution first. All right, so here it says, find the length of the cardioid from 1 minus cosine of theta. Now, isn't that the one that we did before that when we graphed it out? Didn't we get a graph that looks something like this? Oh boy, did it go like this? Something. Oh, I'm terrible at drawing these things. I'm going to plug it into my calculator because I think that's the last one that I had in there. So 1 minus cosine of theta. 1 minus cosine of theta. And yes, I started off correctly. So doesn't it go something like this and then come in like that?
Yeah.
So what we want to do is we want to find the length of this arc. Okay, so I guess we can just follow through here. 1 minus cosine of theta is my r value. Dr d theta is just sine of theta. Pretty easy. And then we're just going to do r squared. So 1 minus cosine squared plus sine squared. Again, I'm going to make you guys work on this without a calculator. I would just do f int to get my answer. And the answer is, wow, it just turned out to be 2. Holy cow. That is pretty easy.
So if it asked it to go counterclockwise, would you flip the two? How would you do that?
You mean going this way? I don't
Oh,
think it
sorry.
makes it I don't think it makes a difference because the length of the arc is going to be the same regardless if you go one way or the other way. So I don't think it would make a difference. The only thing that you can never switch. You can't ever switch it like this. That is, you can't do that because the bigger number always has to be on the top. So if I saw something like this, the first thing I look at is oh, okay, I've got to change this to this and put a negative out in front, because
Yeah.
you can't have a bigger number on the lower end of your integral. It just doesn't work that way. So you always have to, if you do ever have that, you have to rewrite it, put a negative out in front, and that would do it. But I don't think the curve is going to make much of a difference if you're going to go, you know, negative around or positive around. That curve, the curve's length is going to be the same regardless of which direction you go. So I don't think it's going to change much on there. But the formula is pretty straightforward. I mean, it's just r squared plus dr d theta squared. Plug it into your calculator, get your answer. All right, I think I have only one slide left. All right. Oh. All right, give me my answer. This is too easy.
Oh, pi 10. 6 pi.
6 pi? How did you get 6 pi?
It's half of the circumference of the circle, right?
What are you talking about? What does the graph of this thing look like?
It's a circle.
Yeah, with a radius of 6, isn't it?
Yeah.
How do you find the circumference of a circle?
2 pi r.
So what did you tell me the answer was?
Oh, it's a full circumference of the circle. Oh, okay. Then 12 pi. Oh,
All
okay.
right. 0 to 2 pi goes all the way around the circle.
Gotcha. I took it from 0 to pi.
All right. I was going to say, I thought you had it there.
I hope that's an AP test.
All right. That was it for this week. Next week, so the last 3 weeks, we were just dealing with parametric functions, vectors, and polar coordinates. Are you going to see them on the AP test? Absolutely. You'll see tonight, or when you do your assessment this week, there's a lot of problems that deal with finding the area between a polar curve. That's, you know, when you did AB calculus, you probably had finding the area between two curves. Well, in BC Calc, usually they don't give you an easy one like that. They'll give you one with a polar curve, and you have to find the area between the two curves. Now, next week, we're going to start on the last chapter of this, and it gets difficult. We're dealing with, next week is not so bad, but we're dealing with series and sequences, and then we deal with Taylor series, and we try to find where functions diverge and converge. It gets a little bit hairy after spring break. So next week is the beginning of the last chapter, and then I can't believe how fast this semester is going already. Yeah, we're already in week 7. Crazy. And then next week, after week 8, we have spring break. So then you have a week off, and then we get back into it. All right?
Sounds good.
All right, Caleb, you have a great week.
All right, you too.
Thank you.
Mr. Shanklin.
All right, bye.
Bye.